And we can even push to the string by using this notation here, even though I don't like it, but it's also possible. But over here, we have to pass it a string literal, because this is defined in this standard library. All right, let's see. And of course, over here, sorry, we have to use the push stir method. As you can see, this is compiling. So again, we are pushing a single character. Then we are using here the push stir method, pushing a string literal, and we can also mutate strings like that. Replace can be used to replace substring. Again, we have here a string, and we then can replace some elements inside the string. So we provide as first argument the element we want to replace, in this case dogs, and it should be replaced with cats. So S1 should then hold I like cats. Now again, replace will mutate the string, meaning the S should be mutable. More string methods can be found under string module. So number 6, you can only concat a string with a string slice, and strings ownership can be moved to another variable. So we have here S1 holding a string and S2 also holding a string. Now, as you can see, we want to concatenate these two strings, and we can use the plus operator for that. Now, in the Rust documentation, it says that the first argument should be of type string, while all other arguments must be string slices. So we have to convert S2 over here to a string slice. Now, there are two possibilities. The first one is using the stir method like that. So this over here will then be considered as a string slice. So we have converted a string to a string slice, right? But the result of this concatenation will be of type string. It's important to remember that. And S3 should then hold these concatenated strings. Now, because S1 over here has been moved inside S3, we can't use S1 anymore, because S3 has become the owner of this data. So let's instead print out S3. And as you can see, this is compiling. Now, there is an easier approach to that. We can convert a string to a string slice by just providing a reference to a string. So a reference to a string can be inferred to a string slice like that. String slice and string. Opposite to the seldom using of stir, string slice and string are used everywhere. String slice can be converted to string in two ways. So we have covered that. Fix error with at least two solutions. So over here we have a string slice, right? Now we call the greetings function over here with an argument of s. Now s should actually be of type string. So we can convert that by calling this toString method like that. So we have converted here a string slice to a string. All right. The second way would be doing it like that, string from, and then providing s. As you can see, this is compiling. And there are other ways, for example, toOwned, even though I think this is not used that much because it's more general, but it's also possible. Alright, we can use string from or toString to convert a string slice to a string. Use two approaches to fix the error and without adding a new line. As you can see, we have here a string literal that has been put into a string. So this variable over here will hold a type of string. Now to convert this s over here into a string slice, because this is the type annotation of this variable, we can, as I did before, we can pass s as a reference. And again, a reference to a string will be inferred to a string slice. And again, we can use s_stir, for example. It would be the same. String escapes. You can use escapes to write bytes by their hexadecimal values. Fill the blank below to show I'm writing Rust. So as you can see, we can escape certain values and they will then be converted to ASCII characters. For example, this would be the hexadecimal representation of the ASCII value of S, right? So if we want to write Rust here, then the next character to S would be T. So we would write X74 like that. And you can check this out over here. There are a lot of examples where you can just escape using the backslash. Now using two backslashes here will print out these literal characters. So the output will be \x3f, okay? Because we are basically escaping this backslash. All right, and over here we have raw string, and a raw string is a string in which there are no escapes. So everything is printed literally as it is written. So the output of this, let me run that. So the output of this would be \x3f. It won't be converted to an ASCII character. So let's see, string index. You can't use index to access a char in a string, but you can use slice, reference to a S1, for example, and the offset. So let's see, we have here a string. And now we want to access the first character. Now in most programming languages this would be possible, but in Rust you have to use string slices, meaning you take a reference to S1 and then provide the offset. If we want to only access the first character, we would provide an offset in form of a range from 0 to 1. Now again, in a range this would be excluded, meaning we only access this first element. So the return type will then be a string slice. Notice something here. When we assert age, we would have a string of age and not a character. Even though we are here only accessing a character, we are accessing it using the string slice notation over here. So remember, a string slice is just a view into a heap allocated string, right? So we are just looking what is at this location. In this case, we just want to access the first location over here. right? Modify this line to fix the error. Tips. This would take 3 bytes in UTF-8 format. And that's right, we have said that a character in Rust is of size 4 bytes. Now a character in a string is a little bit different. So if it is an ASCII character, then it will usually take 1 byte. And these Unicode characters can take 3 bytes, or I guess some of them even 4 bytes. Alright, so we want to have in H1 only this character. So again, we are taking a reference to S1 and providing an offset. So H would be at index 0, I would be at index 1, this comma index 2, and then this will be index 3. Now this takes up 3 bytes, so we have to provide here an offset from 3 to 6. Remember, 6 is excluded, so it goes from 3 to 5. 3, 4, 5. 3 bytes. Let me output that. As you can see, this would be the output. And again, this is just a view into a heap allocated string, right? Operate on UTF-8 string. Fill the blank to print each character in this string. So over here, there is a method called chars. Now chars will put this sequence of characters into an iterator, meaning we can then iterate over it using a for loop, for example. And that means C will then be in each iteration one of these characters, and we will then just print out C. As you can see, in each iteration we are printing out a single character. Alright, that's it. See you in the next topic. So we'll now cover arrays. Now an array is a fixed size collection of elements of the same data type stored as contiguous block in stack memory. Now it's stored in stack memory because its size is known at compile time. The signature of an array is like that, you can see over here, which indicates that the length is fixed at compile time. Arrays can neither grow nor shrink, they must retain their size. So let's see. The type of array is like this. As you can see, array's length is part of their type signature, so their length must be known at compile time. For example, you can't initialize an array like below. This would not be possible. As you can see, we have an init_r function which takes an argument of type i32. And then we try over here to initialize an array with the length that is provided as an argument. Now this would be a compiler error because, as we've seen, the size of an array must be known at compile time. If we do it like that, the size of the array would only be known at runtime. This will cause an error because the compiler has no idea of the exact size of the array at compile time. Let's see, fill the blank with proper array type. As you can see, we have here an array with 5 elements. Now what would be the type of these elements? It would be the default integer type, which is i32. So we annotate arrays like that in square brackets. Then we would have the type of the elements and the amount of elements inside of the array, which is 5. Modify the code below to make it work. So we can call the len method on an array, and it will then provide the length of the array. So in this case, this would be 5, right? Because there are 5 elements inside. Number 2, we can ignore parts of the array type or even the whole type, let the compiler infer it for us. So we actually don't have to annotate the type, or we can annotate the type but leave, for example, the type annotation here for the compiler to infer. Fill the blank. Arrays are stack allocated. Size of val returns the bytes which an array occupies. A char takes 4 bytes in Rust, Unicode char. So we have seen that before. The size of val will just take an argument and it will output the size in bytes the provided argument occupies in memory. So if we provide the R over here, then we should actually get back 3 times 4 bytes because a character in Rust takes 4 bytes, meaning this array over here would occupy 12 bytes in memory. All elements in an array can be initialized to the same value at once. So as you can see, we have here an array which should hold 100 elements. And each element should hold the number 1. Okay, we are here accessing the first element, and this is the notation for accessing elements in an array. In this case, we access the first element at index 0. And the length would be 100. So instead of typing out 100 times 1, we have a shorthand syntax for that. So we can here, first of all, provide the element it should hold. In this case, 1, and we want it to hold 100 elements of this value over here. Number 4, all elements in an array must be of the same type. So as you can see, because when we annotate an array, we actually have to define the type here. In this case, we want integer types, and we have 3 of them. Now, as you can see, this is a char, and this is not possible. All elements inside an array must be of the same type. Indexing starts at 0. So over here we have an array of characters. Let's annotate that. And there are 3 elements inside it. And now we want to access the first element, right? We want this variable over here to hold the first element. Now again, arrays are 0 indexed, meaning we access it using this notation here and provided a value of 0. Out of bounds indexing causes panic. So over here we have an array which holds 2 strings, and we want to access the first element, right? Now we can use this notation over here like we did before, or we could use the get method. The difference is that get will return an option type. We'll cover that in a later episode, but it's generally safer than using this notation. And this is especially true if you're accessing elements at runtime, okay? So we can use this notation, or we could use this notation. Now over here this would panic because this array has only 2 elements, meaning indexes 0 and 1. So let's access here index 1. and this compiles. So let's see slices. A slice is a reference to a contiguous sequence of elements in a collection. It provides a way to borrow part of a collection without taking ownership of the entire collection. It can be created from arrays, vectors, strings, and other collections implementing the deref trait. So let's see this example of a slice. We have here an array. And then we are over here taking a reference to A and providing an offset. Essentially the same thing we did with string slices, right? A slice is just a view into a collection. And over here we try to access the elements at index 1 to index 2, right? Because 3 would be excluded. So the variable slice will then hold a slice with the elements 2 and 3 in it. Right, let's see. Slices are similar to arrays, but their length is not known at compile time, so you can't use slice directly. Here, both this slice over here and stir are slice types, but directly using it will cause errors. You have to use the reference of the slice instead. So because these two slices over here, their sizes are not known at compile time, we have to use a pointer to that, right? And we have seen that in the example of string slices. So we use this syntax over here. Fix the errors, don't add new lines. As you can see, we are holding here an array. Let's annotate the type like that. And this is an array of 3 i32 integers. Now we want here to get a slice with this offset, meaning from 0 to 1, 0, 1. So again, like we did with a string slice, we want a reference to an array with this specific offset. So we are trying to access 0 to 1 because 2 is excluded, meaning we are accessing here index 0 and 1, the elements 1 and 2. So this slice over here will then hold 1 and 2, right? Now the type annotation here would be like that because we are holding a reference to this array, right? And this would be the type annotation of a slice. Now over here we have a string literal. Now string literals, as we've seen, always are annotated like that. String literal is hard-coded into the program's binary, and that's why we can access it using a reference to this string literal over here, which is in the binary itself. All right. A slice reference is a two-word object. For simplicity reasons, from now on we will use slice instead of slice reference. The first word is a pointer to the data and the second word is the length of the slice. The word size is the same as usize determined by the processor architecture. For example, 64 bits on an x86-64. Slices can be used to borrow a section of an array and have the type signature like this, where T over here stands for the type. As you can see, we have here an array with 3 characters. Now we want to have a slice of this array with the first 2 elements, these 2 elements. And this is shorthand notation. Instead of writing it like that, we can just omit the 0. Alright? So we are accessing 0, 1, and 2 is excluded. So the slice variable should hold a slice with these elements. The type annotation over here would be reference to char. Okay. Modify 8 to make it work. Tips slice reference is not an array. If it is an array, then assert will be passed. Each of the two characters, this and this, occupies 4 bytes. 2 times 4, 8. Now, because the slice variable over here doesn't actually hold an array, but a slice, we are here actually holding a pointer, right? Because this is a reference to this array. And that means we have seen over here a slice reference is a two-word object, meaning the pointer and the length field will both occupy sizes of type usize. And usize, if you're on a 64-bit computer, it means usize will be of size 8 bytes or 64 bits. And that's why a slice holds 16 bytes, right? If we would pass the array here, we would have, if this slice would have been an array, then 8 would actually pass, because we would have two characters. Each character is 4 bytes, meaning 8 bytes. But because we have a slice which holds a pointer and a length, both of type usize, we have 16. So over here we have an array of 5 integers of type i32. Fill the blanks to make the code work. As you can see, we want the slice variable to hold a slice of these elements. So let's first annotate the type actually. So the slice variable over here should hold a slice of i32 elements, right? So we are taking a reference to the array and provided an offset. We want to go from this to this, meaning index 0, 1. We are starting at 1 and we go up to 0, 1, 2, 3, 4. And I choose 4 here because 4 is excluded. So we will go from 0, 1, 2, 3 to index 3. String slices. And we have covered that already, but let's do some exercises for repetition. Now over here we have a string and we take over here a string slice, meaning we take only the first two characters. Like that. Or let me write it like that, right? We take the first two characters. Fill the blank to make the code work. Don't use 0 to 2 again. So over here we have a second variable which should hold a string slice, and they should actually hold the same elements. As you can see over here, we are here asserting that slice 1 and slice 2 are the same. So instead of using this syntax over here, as we've seen before, we can use like that. We can omit the 0. Over here we have a string literal. Again, a string literal is hard-coded into the binary, and this would be the type annotation. Modify this line to make the code work. As you can see, we want slice over here to hold a string slice with only this character. So let's annotate the type. This would be a string slice. And because this Unicode character over here takes 3 bytes, we have to provide an offset here of 3, meaning 0, 1, 2, right? 3 bytes. Alright, last one. Number 6, a reference to a string can be implicitly converted into a string slice. Now over here we initialize a variable s, which holds a string. Here reference to s is reference to string type, but first word needs a string slice, as you can see over here. It works because reference to string can be implicitly converted to string slice. So as you can see over here, we are calling the first word function, which takes as an argument a type of string slice. And this would actually work because we are here providing a reference to s, which means this over here is a reference to a string, right? And a reference to a string can be converted to a string slice implicitly by the compiler. So then this function over here will take a reference of s and provides an offset from 0 to 1, where 1 is excluded, so we just take the first element. And it returns this as a string slice. That means that the return value of this function will be assigned to the word variable. Then over here we are calling the clear method on s, which means the string will then be empty. Clear will just remove every content in the string. The string itself will still remain in memory with the same capacity, and s also is valid, so it's different from drop, but it will empty the string essentially. So we will then have over here an empty string. The problem over here is that clear takes immutable reference to self. And that's a problem because over here we have a reference which is immutable to s, and we have over here a mutable reference to s. Now the problem arises because we are here using the immutable reference. So if we would delete that and put it over here, then after this point the word variable over here, which holds an immutable reference, is not used anymore, and so we can use this clear method. And this is compiling, and as you can see we just get the first element. Alright, see you in the next topic. Now we will cover tuples. We have seen some tuples before in some exercises, but now we will go into greater detail. So a tuple is a way to store related pieces of information in a single variable. And it's essentially a collection of values of different types grouped together as a single compound value. Again, a compound value is a type composed of other types. It's stored as a fixed size contiguous block of memory on the stack, and the signature is parentheses and the types the tuple is holding. Let's see. Elements in a tuple can have different types. Tuple's type signature is like that, where T1, T2 are the types of tuple's members. So as you can see, we can hold different types. We have here an U8 and an I16 together in a tuple. Tuples can be tuples members. So we can even nest tuples. So this tuple over here, as you can see, holds an U8 over here and another tuple inside it, which holds an I16 and a U32 integer. Alright? Fill the blanks to make the code work. So over here we have to annotate the type. Now again, the first element over here would be U8. The second one is U16. The third one is an I64. The fourth one would be a string literal. And the last one is a string. Members can be extracted from the tuple using indexing. So as you can see, we have here a tuple. Let's annotate the type. This is how we would annotate a tuple, and it holds 3 string literals. Then we are accessing here the second element. Tuples, remember, are 0 indexed. But in this case, it would be M. But we want it to equal sun phase. So we have to access the index 2, right? 0, 1, 2. Long tuples cannot be printed. So if a tuple exceeds a certain amount of elements, it is too long to be printed. As you can see, this would be too long. If I delete that over here, so this would work. So we can have up to 12 elements in a tuple to make it printable. If it exceeds 12 elements, you can still use it, but it's not printable. Destructuring tuple with pattern. So let's first annotate the type of this tuple here. We have an I32, the default integer type. Then we have a float, which means F64, the default floating point type, and we have a string literal. Fill the blank to make the code work. So over here we want to destructure this tuple, where X holds 1, Y holds hello, and Z holds 6.4. So let's see. We destructure tuples like this using the let keyword and the parentheses. Then the first element should be X, right? Now the second element, 6.4, should be put into Z. And the last element should be destructured into variable Y. Destructure assignments. Over here we are declaring some variables, and then over here we destructure this tuple and we want to put it inside these variables. So because we have already declared these variables, we don't need to declare it once more. So we can omit the let keyword. And then all we do is we destructure it. So 1 should be put inside variable Y. 2 should be put inside variable Z. And 3 should be put inside variable X. Tuples can be used as function arguments and return values. Fill the blank, need a few computations here. So as you can see, we are calling this function sum multiply, and this function over here expects an argument of type tuple, and the tuple should hold 2 integer values. What we do over here is we perform some operations and return it in a tuple, right? So the first operation will be this one. adding the first element of the provided tuple with the second element of the provided tuple, and then we are multiplying the first element of the provided tuple with the second element of the provided tuple, and we return that in a tuple again. So the result of this operation over here will be the first element, and the result of this operation will be the second element. And as you can see, we can return that in a tuple. Now, after returning this tuple, we destructure it. So the first element will be put in X, and the second element will be destructured to the variable Y, where X will hold 5 and Y will hold 6. So we have now to provide here two numbers. When we add them together, they will evaluate to 5. If we multiply the two numbers, they will evaluate to 6. So this is a little riddle for you, and try to solve it. And the answer would be 2, 3, right? And don't forget to add here parentheses, because we are passing it here a tuple, right? We are not passing two arguments, we are passing one argument, which is a tuple that holds two elements. Very important. So if we add 2 and 3, we will get 5, and if we multiply 2 times 3, we will get 6. And this will be the return type of this tuple over here. Alright, see you in the next topic. Up until now we have been using types that are defined in the standard library, but we can in fact create our own types. And we can do that by using a struct. Now a struct is a compound type allowing to group together values of different types into a named data structure. It's similar to tuples, but each value has a name, so the values can then be accessed through this name. And a struct has to be instantiated with data. Think of it like the struct itself is the template for the instances you create from it. Now let's see how that works. As you can see over here, we have our template. In this case, a struct named user. And the user struct holds various fields. And we can define a field by giving it a name and a type that this field should hold. So in this case, the active field holds a type of Boolean. Username holds a type of string, email string, and sign-in count U64. And then we can instantiate this struct. And we do that by calling the name of the struct, user in this case, and providing for each field a concrete type. And of course, the types have to match the template. Then we are assigning this instance we have created over here to a variable. So this variable will then hold an instance of the user struct. And we can access and even mutate the fields of an instance. So over here, as you can see, we have created an instance and assigned it to the user1 variable. And then we can use this syntax over here to access a field. So in this case, we are even mutating the email field from the instance user1. As you can see, we do that exactly like we would mutate a variable, just assigning it a new value. Now, to mutate, you have to make it explicitly mutable, meaning you use the mute keyword here like you did with variables. And functions can also create instances and return it. So in this case, we have the build user function, which creates an instance of the user struct. And as you can see, again, it's just providing concrete values for each of its fields. And over here, as you can see, this function takes two arguments, email of type string and username of type string. And then it provides it to the username field and to the email field. Now in this case we are repeating ourselves, as you can see. And we can avoid this by just using this shorthand syntax. So if the name of a field and the name of a variable or argument matches, then we can write it like that. And this just makes it less verbose. And there is also a concept called struct update syntax. So over here we have an instance of the user struct. Now we want to create another instance, but taking some of the values from the fields from user1. As you can see, for example, in this instance, we want the active field to hold the value of user1's active field. So we are accessing user1 and the active field. And as you can see, we are taking everything from this user1 instance except the email. And as I've said, there is a better way to write this, and this would be instantiating a struct like we did before, but just providing the fields that are different from the instance we want to take from it. So for example, over here we say that the email field should hold this value, and the remaining values should be taken from this user1 instance. So this will then create a user instance with all the same values from user1 except the email field. Then we also have tuple structs. And tuple structs are like normal structs, but using tuple-like syntax for defining their fields. It's basically a named tuple, and it's instantiated by parentheses instead of curly braces. And its values are accessed using point notation. And then we have unit-like structs, and these are structs without any fields, meaning they don't hold any values. And it's mainly used when working with traits, and this will be covered soon. And that means they don't store any data. Let's solve some exercises, the types of structs. Exercise 1, we must specify concrete values for each of the fields in the struct. As you can see, we have here a person struct holding various fields. And then over here we have a variable age, which holds a value of 30. Now then we are instantiating this person struct and assign it to the variable p, meaning p will then be an instance of the person struct. Now as you can see, we have here the fields and the concrete values. And this would be the shorthand syntax for this, because we have over here a variable matching the name of the field. So we can write it like that. But as you've noticed, we didn't provide the hobby field a concrete value. So when you are instantiating a struct, you have to provide to each field a concrete value. So let's do that. And the variable p will then hold a type of person. Now age, of course, has to match with the template, so this would be an U8. And of course, we use commas here and not semicolons. Alright, unit struct doesn't have any field. It can be useful when you need to implement a trait on some type, but don't have any data that you want to store in the type itself. So as you can see, this example is using traits, and we have not yet covered that, so I will skip that because this might just be confusing, and we will cover that soon. Number 3. Tuple struct looks similar to tuples. It has added meaning the struct name provides but has no named fields. It's useful when you want to give the whole tuple a name but don't care about the fields' names. So as you can see over here, we have two tuple structs, one color and one point. And they are exactly like tuples, but they are named. Okay, so over here we have three integer values in the color tuple struct, and in the point struct the same thing. Now we want to instantiate the point struct over here, and the variable v will then hold an instance of our custom type point. Then we are calling the checkColor function and provide an argument of v. Now as you can see, the checkColor function takes an argument of type color, but this is not what we want, right? Because we are here passing a variable of type point. So let's change that. And over here we are then destructuring the instance that was passed. So in this case, as you can see, x should hold 0. So let's provide this value over here. Then the p1 field, and as you can see, we are accessing the fields in the tuple struct like we would access elements in a normal tuple using this syntax. So over here we are accessing the second element, and this should hold 127. So that means the last element should hold 255. And as you can see over here, we are destructuring. So the first element over here gets destructured into a variable x. Now the second one over here, we don't need to destructure, right? Because we are accessing it directly using the p instance. And the last one, let's call this z, okay? And by the way, when destructuring and you don't need a value, like for example this one, you just provide it an underscore. Let's see. And of course, when destructuring, we have to provide the name of the struct, in this case point. And this is compiling. Operating on structs. You can make a whole struct mutable when instantiating it, but Rust doesn't allow us to mark only certain fields as mutable. Fill the blank and fix the error without adding, removing new line. Again, we have the person struct. We have here the age variable. Let's annotate that, and we have the p instance. So as you can see, we want to mutate the age field of the p instance. And this is right, but the problem is the p instance is not mutable. So let's make that mutable. And then we can also mutate the name field like that. Using field init shorthand syntax to reduce repetitions. So again, we have the person struct, and in main we are just printing out something. And over here we have the build person function. So as you can see, this function takes two arguments, name of type string and age of type U8. And these arguments exactly match the types defined in the template. So then we can over here instantiate a person struct meaning we can here for the name field provide this argument. And we have seen we can use field init shorthand syntax, meaning if the field name matches the name of a variable or an argument, we can skip it like that. Let's see exercise 6. You can create an instance from another instance with struct update syntax. So as you can see, we have here the user struct, and we have seen an example of that in these slides. Then over here, we are creating an instance from the user struct. That means the variable u1 will then hold an instance. That means that the variable u1 will then be an instance of the user type. And again, we are just providing each field over here with a concrete value. Then over here, we call the setEmail function with an argument of the u1 instance. So let's see over here, as you can see in the function signature, the argument must be of type user. And then we want to create over here a new instance. And what we want to achieve here is that we take every field from the u1 instance except for the email field. We want that to be different. So what we can do is providing a concrete value for the email field and then just saying the rest we want to take from the argument provided. And then we are just returning it. So that means u2 will then hold a newly created instance. Print the structs. We can use derive debug to make a struct printable. Fill the blanks to make the code work. So you actually can't print out a struct using the normal print line syntax. So to be able to print a struct, we have to derive a trait. Again, we will cover traits, but we have to derive that using an attribute. All right. That means that the struct rectangle here implements this debug trait. And that means we can then use debug notation to print it out. So over here, as you can see, we have a variable scale, and then we are creating here a rectangle instance. So we are providing a concrete value for the field width, and this would be 30 times the scale. And we provide a concrete value for height. Now, as you can see, print debug info to standard error and assign the value of 30 times scale to width. Now, this debug macro over here will just print out debug information to the standard error output. And that means over here, rect1 will then hold an instance of the type rectangle. And the type annotation for the scale variable over here would be u32, right? Because we are passing this scale variable over here, meaning it should be of type u32. And then again, we are here using the debug macro and printing out rect1. And instead of doing that, we can also use a normal print line statement like you're used to, except that in the placeholder over here, we have to use this notation, and this is called debug notation, meaning any type that implements the debug trait can then be printed. And the difference between debug macro and printline macro, as you can see, printline will print to the standard output, while debug will print to the standard error. And that's why you don't see it over here. You just see the printline output. Now to see that, I will go to the Rust playground. And we can just run this code. And as you can see over here, this would be the debug output. So this debug macro over here prints out the exact thing we are passing to the width field. In this case, 60. And this debug macro over here prints out the instance, right? We then have a rectangle with a width of 60 and a height of 50. Basically the same thing that we print out with the print line statement here. Partial move within the destructuring of a single variable, both by move and by reference pattern bindings, can be used at the same time. Doing this will result in a partial move of the variable, which means that parts of the variable will be moved while other parts stay. In such a case, the parent variable cannot be used afterwards as a whole. However, the parts that are only referenced and not moved can still be used. And I guess we have seen that before, but let's do another exercise. So as you can see, right, we have seen that. All right, so let's move to the exercises directly because I've already covered that. And I think the exercises are better for understanding. So as you can see, fix the errors to make it work. Over here, we have a file struct holding two fields of type string. Then in main, we are creating an instance of the file struct, providing it concrete values for each field, meaning f will then hold an instance of the file struct. And over here, we are then assigning the name field of the f instance to the underscore name variable. So what would be the type annotation here? It would be string, right? Because f name holds a string. And that means the name variable here will become the owner of this string data. And that is the reason that we then cannot use f as a whole and also not f.name, because a partial move happened. So if a field gets moved out to another owner, then you can't access this field and also not the data structure that is holding this field. So this would fail over here and this would fail. Now to fix that, we can actually access just the name variable here, right? Because this is now the owner of this string. But what we can't do is accessing the whole instance over here. This is not possible. As you can see, this is working. Now, if you actually want to keep f as the owner of all the fields and to print it out like that, and by the way, notice again, when we are outputting a single field, we use the normal notation. If we output the whole instance, then we have to use debug notation, because these fields over here hold types that are defined in the standard library, while this is a custom type we have created. So to make that work, we can also use here the clone method. And as you can see, this is working and we are here printing out the instance. All right, see you in the next topic. We can also create custom types using enums. Now an enum is a way of defining a type with only one of a possible set of values. We can only access one variant of an enum at a time, and it can hold additional information using tuples. And it's especially useful when using in match statements. Let's see an example of an enum. So we have here the enum IP address, and this enum holds two variants. So in enums we call it variants and not fields like in structs. And each variant over here holds a type using tuple-like syntax. Alright, so an IP address, by the way, can be in either one of two formats. Either it's v4 or v6. And now we will see the difference between enums and structs. So this is how we would instantiate this enum IP address. We are accessing the name of the enum, double colon, and then the name of the variant, in this case v4, then providing it a concrete value. I hope you noticed the difference. In a struct we would have provided concrete values for each field. In an enum we instantiate the enum only with one single variant. Alright, so this home variable will then hold an instance of the IP address enum, and this loopback variable over here will also hold an instance of IP address, but using the variant v6. And by the way, this is the old format of IP addresses and this is the new one. So let's do some exercises. Enums can be created with an explicit discriminator. So enums are enumerated, right? That's why they are called enum. Now, if you don't provide here a value, it will be implicitly starting from 0. This would be 1 and this would be 2. And we can also enumerate them with an explicit discriminator. Okay, so this will then hold 0, this variant will be 1, and this will be 2. And over here you can see C like enum. Now you can't use as a discriminator a floating point value. This is not allowed. But like in C, if you for example would do it like that, we are here providing the discriminator 5. Then 1 and 2 implicitly will be 6 and 7, right? Or we could say this should be 9, for example, right? So you can manipulate the enumeration of an enum. So let's see actually. Let me change that back and let me change that to integers. An enum variant can be converted to an integer by the as keyword. So when we take this enum over here and we create an instance, as we've said, as we've seen, calling the name of the enum and the variant, and then we can convert it to an U8, for example, right? And we can do the same thing here, and over here it should be the same thing. And as you can see, this is compiling. Let me print out. As you can see, when we access from the number enum the variant 1, then a 1 will get outputted. Now let's see if I provided a value of 10 over here. But for that I have to comment that out. As you can see, this would then be the discriminator for the one variant. Alright, each enum variant can hold its own data. So as you can see, we have here an enum message. Now this enum has different variants. So this variant quit doesn't hold any additional data. While this variant move here holds fields. It's very struct-like. And this variant write is tuple-like. So it holds a value in a tuple syntax, and the same thing for change color. So we can then instantiate the move variant from the message enum with these values over here, x1 and y2. And as you can see, because this is very struct-like, you instantiate it basically like a struct. And over here, instantiating with hello world. As you can see, this variant over here holds a string type. So like that. And please notice over here that both of these variables here hold the same type, message. Because this is also a custom type, a type we have created. We can get the data which an enum variant is holding by pattern matching. So over here we have the same enum like we saw before, and over here we have an instance of the move variant. Now we can here use if let, and we will cover that in the next section, to get out the data inside this move variant. So we are matching here the message variable holding an instance of the move variant, and then over here we can basically destructure it. So x should then be destructured into a variable a, and y should be destructured into a variable b. And then, as you can see, we can use these two variables. Now we are here asserting a and b, and a stands for this value and b stands for this value. And as you notice, they are not the same, so this would fail actually. So let me change that, and now let's run the program. Fill in the blank and fix the errors. Again, same enum, and over here we have an array of different variants from this enum type, right? We have the quit variant, the move variant, and the change color variant. Now the neat thing here is that all of these instances are of the same type, message, right? Our custom type. Now I hope you remember how we annotate an array. So first thing will be the type and then the number of elements. Let's see, we have over here 3 elements, right? And the type would be, I hope you know it, message, right? All of these variants or instances hold the same type. And then over here we are looping over this array here, meaning message, this variable, will hold in each iteration one of these instances, and then passing it to the show message function. And as you can see, when we want to take an instance of this enum message, we can just use the type message here, because again, all of them have the same type. And all we do then is just printing it out. And again, because this is a custom type, we cannot print it out just like that. So we have to use debug notation here and derive over here the debug trait. And as you can see, in each iteration over here, we call the show message function and it will print out the contents of this array. So let's see exercise 5. Since there is no null in Rust, we have to use enum option to deal with the cases when the value is absent. And I want to show you some slides for that. So the option enum. Option is an enum that represents a value that may or may not be present. It's known in other languages as null and it's referring to the absence of a value. It's used to handle cases where a function or method might fail to return a value. So this is how the enum option looks like as defined by the standard library. As you can see, it's an enum holding two variants, none and some. Now this over here is a generic, meaning that some can hold any type, and we'll cover generics very soon. But for now, again, think that this can hold any type provided. So let's see an example over here. We are here initializing the variable 5 with the variant sum holding an integer value, right? And then over here, we are calling the function +1, providing it 5. So let's see here. As you can see, the argument should be of type option, and the type parameter here would be i32. Now we have to provide a concrete type for this generic type parameter. Now again, we will cover that in much greater detail, but as you can see, this is exactly the type we are passing to the function. Sum is a variant of the option enum, and it is holding an i32 value, and it is holding an i32 type. Now then we are matching this argument over here. If it is holding a none, we will return none. If it is holding a sum, then over here we are destructuring the value wrapped inside this sum variant into the variable I. And then over here we are incrementing I by 1 and wrapping it in a sum. Because as you can see, the return type over here is defined as option i32. And that means that this variable over here will then hold sum 6, right? Because we have incremented 5 over here by 1. So this will hold an option type, and the concrete value would be sum 6, the sum variant, and a value of 6. Now over here we are calling the +1 function with none, meaning the argument will get matched and this will then get returned, right? A none. And as you can see, the none is also a variant of the option enum. And this i32 just stands for the sum variant. If we are returning none, then this type over here is still valid, because the none variant here doesn't hold any value of generic type T. But again, generics are a topic on its own. And by the way, this is exactly the same that we have over here. So let's do that, annotating the types. So over here we have an option holding an i32 type. All right. And as I've said, this is not necessary. You can omit that because again, the option type is in the prelude. Then we are calling the +1 function. Again, we are providing it sum5, which is an option, and then we are matching the argument. So if the argument is none, then we return none. If it is sum, then we destructure the value that was passed over here, and we increment it by 1 and return it wrapped in sum, because the return type has to be of type option. That means over here the type annotation would be option I32. And in this case we are passing a none, so a none will be returned. And by the way, the returned value here would be sum6, right? Because 5 plus 1 will be 6. And over here we have none, and the type annotation would still be option I32. Now we want actually to unwrap this value inside the sum variant, and we can do that by using if let. So as you can see, we are matching the 6 variable holding sum6, and then we can destructure it basically. So we can then say sum and the variable n, meaning we then can use n over here. And I see right now never let this run, so we have to pack that into an else block. Just to ensure that this doesn't run after we are running this conditional here. And as you can see, it will output the value inside sum. Now again, we'll cover generics, we'll cover if let and match over here. This will actually be the next topic. So don't worry if this seems a little difficult to understand, we will cover that in much greater detail. Implement a linked list via enums. Now over here, this linked list I won't cover because there are a lot of things we haven't seen. So in here we have methods and other things that we didn't really cover. So I think this would be more confusing than it would be helpful. What I suggest you is that you will come back after we have seen some more topics. You come back to this exercise and try to solve it. It's not that difficult, and the solution will be on my GitHub account, but I think this is just overkill right now. So see you in the next topic. The normal flow of execution in a program would be from top to bottom, line by line, but we can actually manipulate the flow of a program. And flow control is a concept that refers to the ability to control the order in which statements or instructions are executed in a program. It allows to specify which instructions should be executed under which conditions and in what order. So we have many ways to do that, and some of them are, for example, using conditionals. So we have the if-else keywords and match, for example, and we can use loops, for loops, while loops. There is a special loop in Rust called loop, we'll cover that. And we can even manipulate the flow inside the loop by keywords such as continue and break. So let's see. So let's start with if-else conditionals. Over here we are initializing n with a value of 5. Then over here we have an if conditional, checking if n is less than 0. In this case, this would evaluate to false, meaning this instruction over here will get ignored and the program will continue executing on the next line. Now in the next line we have another conditional. So we can use here the else if keyword. And over here we are checking, is n bigger than 0? In this case, this would evaluate to true, meaning this line will get printed out. Now, we can also match anything else using the else keyword. Meaning, if this evaluates to false and this evaluates to false, then this will get executed. Now in this case, this evaluates to true, so this will get executed, meaning this over here will be ignored. As you can see, this was the line that has been printed out. Number 2, if-else expression can be used in assignments. Again, initializing n. And over here we have a variable assignment. Now we can even use if-else conditionals when assigning a value to a variable. Now remember, a variable assignment is a statement, so we have to end that with a semicolon like that. So let's see, we have here an if conditional, and this is a Boolean AND operation. Do you remember? We have two inputs, and both of these inputs have to evaluate to true in order the AND operation to return true. So let's see, we have here n should be less than 10, which would evaluate to true, right? Because 5 is less than 10. And 5 is bigger than minus 10. So this AND operation will return true, meaning the code in this if conditional block will get executed. And over here we are just printing out a line, and then we are multiplying n by 10. And in fact we don't have a semicolon, so this will be returned from this expression, meaning it will then be assigned to the variable big N. So big N will then hold a type of i32. Now in case this would evaluate to false, then this else block would get executed, meaning again we are printing out a line and then dividing n by 2.0. Now as you can see, we should omit this semicolon because this result over here should then be assigned to this variable. Now we actually can't do this operation here because n is of type i32 and we are dividing it by a floating point number. So we can typecast that to an i32. And as you can see, this would be the output, and we are printing out big N, meaning 50 over here. So N has been multiplied by 10. So let's see, we have here a for loop. The for in construct can be used to iterate through an iterator, for example, arrange A to B. Now, as you can see, we have a for loop declaring a variable n, and we provide a range. Now, this range over here reaches from 1 to 100, and 100 here included because we have here the equal sign. Then we are checking if n is equal to 100, this program will panic. That's not what we want. So what we can do over here is just removing this equal sign, because that means 100 is excluded, meaning n will never be equals to 100. The largest it will get will be 99. Let's see. All right. Fix the errors without adding or removing lines. So over here we have an array holding two strings. Now we want then to iterate over this array, meaning this name variable will hold in the first iteration this string and in the second iteration this string. So what we can do over here is printing out name, right? So this will iterate 2 times and it will output this and then this. Now, as you can see, we are trying to access names again over here. And that would then violate the ownership rules, because as you can see in a for loop, the for loop actually will take ownership of the provided value. And we can pass here a reference like we have seen before, and that means we can use names then again. So, and by the way, we don't have to dereference name over here because the print line statement will do that automatically. Now over here we have 3 i32 integers. The elements in numbers are copies, so there is no move here. So we are iterating over each element in this array, where n will then hold in each iteration 1 element from this array. So let's see. So, and this would be the output. As you can see, in the first iteration, name will hold this string, and in the second iteration, it will hold this string, and it prints it out in each iteration. Then we print out the whole array, and over here the same thing but with the integers. So again we have an array. So iterate the indexing and value in A. So there is a useful method called enumerate. And this enumerate method takes a collection, for example an array or a tuple or anything else, and it will then return a tuple. And this tuple will then hold the index and the value. Meaning, for example, in the first iteration, this tuple will hold for I 0 and for v 4, right? Because at index 0 we have a value of 4. And it will then just print out the index, but we increment it by 1 and the actual value. And of course, we have to put A into an iterator. So let's see. Like that. So we have to first put A into an iterator, and then we can call this enumerate method on it, because the enumerate method is implemented in the iterator trait. We'll take a look at that later. So as you can see, this will be the output. And that was the reason we have incremented I by 1, because we don't want to start with the 0th element is 4, right? So we say here the first element is 4, second 3, and so on. While. The while keyword can be used to run a loop when a condition is true. Fill in the blanks to make the last println work. So as you can see, we have here a mutable variable n. Loop while the condition is true. So as you can see, this is a while loop, and we provided a conditional, meaning if this evaluates to true, then this loop will keep running until this conditional evaluates to false. So inside the while loop, we have other conditionals. As you can see, we here check the condition n modulus 15 is 0. If that would evaluate to true, then we print out that. And by the way, this was a question at coding interviews at Google. So we are here having more conditionals and an else conditional. So meaning if anything of this fails, then this will get printed out. So what we can do over here, checking if n is less than 10, then this loop will keep running. Now when you're using while loops, then you have to ensure that the while loop eventually stops, right? That this conditional over here will evaluate to false eventually, because otherwise you would have an infinite loop. Now to do that, we can increment n over here. So I increment at the end of this while loop n by 1, meaning in each iteration in this while loop, n gets incremented by 1. So n will eventually be bigger or equal to 10, meaning this would evaluate to false, meaning we break out of this loop. Continue and break. Use break to break the loop. So we have here a for loop looping from 0 to 100 and 100 included. So if n is 66, then we want to break out of the loop. And the break keyword will immediately exit out of this for loop. So when this conditional evaluates to true, we immediately exit out, meaning the program will continue execution after the for loop. In this case, this line over here. Let's see. So as you can see, in the end, n will be equal to 66. Because when I is 66, then we stop iterating. Continue will skip over the remaining code in current iteration and go to the next iteration. So as you can see, we are here again iterating from 0 to 100, and we have here an if conditional. If n is not equal to 66, then we increment n by 1. And we want then to continue, meaning that the remaining code in this for loop will get ignored. So this continue keyword, the program will go back to the beginning of the for loop. Now in case this evaluates to false, right? So if n is in fact 66, this would evaluate to false, meaning we ignore this code block and we go over here where we want to break out of the loop, because as you can see, we want n to be 66 at the end. Loop is usually used together with break or continue. So loop is a special loop in Rust where this is basically an infinite loop, and you have to manually manipulate the flow of the loop, and we will see soon. So this is an U32 over here, count. So let's count until infinity. As you can see, we are here using the loop keyword, meaning this would keep looping to infinity, or we provide some keywords that will break out of the loop or continue. So as you can see, in each iteration, we are incrementing the count variable by 1. Now, if count is equal to 3, then we print out 3 and we want to skip the rest of this iteration. So we can use here the continue keyword. Meaning, again, the rest over here will be ignored. the program will go back to the beginning of the loop. So then over here, if count is not equal to 3, this will get printed out. So we print out the count in every iteration except if count is equal to 3. And then over here, if count is equal to 5, then we print out, okay, that's enough, and we want to break out. Meaning count in the end should hold a value of 5. As you can see, we are iterating 1, 2, and then in the third iteration, this if conditional evaluates to true, meaning we print out 3, and we continue. We are going back to the beginning. So the actual value of count over here is not printed. As you can see, there is no digit 3, but we printed out 3 over here because that was defined in this code block here. And then at iteration 5, we will stop and break out of the loop. So loop is an expression, so we can use it with break to return a value. And again, we have here a counter. So over here we have a loop, and we are in each iteration incrementing counter by 1. Then we check if counter is equal to 10, then we want to break out. But as you notice, we want to assign a value to the result variable, right? This variable should then hold an i32, but we don't return anything here. So you can define after the break keyword a return value, meaning, for example, we want to return counter. But in this case, result will hold 10, right? Because counter, when we break out, will be 10. Otherwise, this conditional would not evaluate to true. So if counter is 10, then we break out. But as you can see, we want result to be 20. So we can even pass here an operation. So we can double the counter value. Let's see. And this is compiling. It's possible to break or continue outer loops when dealing with nested loops. In these cases, the loops must be annotated with some label, and the label must be passed to the break continue statement. So, as you can see, we can even nest different loops. So when we do that, we have to actually provide labels. So we provide here outer for the outer loop and inner one for the inner loop. And as you can see, we have even 2 inner loops. So we have inner 1 and inner 2. All right, so let's see. In the first inner loop, we are checking if count is bigger than or equal to 20. If this is the case, we break out of this inner loop. Otherwise, we increment the count by 2. All right. And notice here, this would break only the inner 1 loop. So when we break out of this loop, this outer loop will still continue looping, okay? So then over here in the outer loop, we are incrementing count by 5. And in this inner 2 loop, we are then checking if count is bigger than or equal to 30, then we break out of the outer loop. Otherwise, if count is smaller than 30, then the outer loop will continue, meaning the program will go back to the beginning of the outer loop and continue executing from here. So let's go step by step. And as you can see, we have to find out here what the count value will be in the end. Okay, let's go step by step. We start at 0. Then over here we are checking, is count bigger than or equal to 20? No, right? So that means count will get incremented by 2. And this will continue because we are in this loop, remember? And this will continue until this evaluates to true, meaning when count is 20, then we break out of this inner loop, meaning we continue executing here. Then count would be 20 and we increment it by 5. Then we enter this inner 2 loop. So 25 is not bigger or not equal to 30, meaning we don't break of outer, but we will continue outer, meaning we go back over here. Now we enter this loop here, and 25 is bigger than 20, so we break out of this inner loop and continue here. Then we add 5 to count, meaning count is now 30. So we enter this inner 2 loop, and this will now evaluate to true because count is equal to 30, meaning we break out of the outer loop. So in this case, count will be 30 in the end. And this succeeded, and I will see you in the next topic. Pattern match is a powerful construct that allows you to compare a value against a set of patterns and then execute different code based on which pattern matches. And these patterns can be made up of literal values, variable names, wildcards, and so on. And in a match statement, all possible cases must be handled, and this is enforced by the compiler. And really, this match keyword is something that I really miss when I'm coding in other languages. So once you get used to it, you will love it, and you will see why. So let's see an example. Over here we have a coin enum, and this enum holds variants of different denominations of US currency or US coins. And here we have a function value in cents. This takes as an argument a variant of type coin. Then it matches the argument, and as you can see, it matches the variance of this coin enum. Meaning, if we provide an instance of this coin enum which holds a penny variant, for example, then it will return 1, right? And this will then be the return value of this function. So for each denomination over here, it will return its proper value. Then let's see if let. So I've said that in a match statement, all possible cases have to be handled. And this could sometimes lead to annoying boilerplate code that is not really that necessary. So for example, we have over here an option type, right? A value wrapped inside sum. And then we match this variable over here that holds this option type. And then we are matching. As you can see, if it is sum, then we destructure the value inside this max variable, and then we just print it out. Now, as you can see, we also have to match any other case, meaning if it is not sum, in that case none, then nothing will get executed, meaning it will return a unit type. Now, this is sometimes too verbose, especially for cases like this. For example, you just want to unwrap something from a sum variant. Now what we can do instead is just using if let. So it's exactly the same as this match statement, but we know that config max holds a some value, right? So we don't have to consider the case where it holds a non-value. And as you can see, this is how we would destructure this value into the variable max. We use the if-let keyword and then the pattern. So if config max holds a sum, then the value will get destructured. Let's do exercises. Fill the blanks. So over here we have a direction enum holding directions over here as variants. Then over here, as you can see, we are instantiating the direction enum with a variant of south. So the type over here would be direction. Then we match this variable here, and if this variable over here holds direction east, then it will print out east. Now we want over here to match south or north. So what we can do over here is pattern matching either south or north, and we can do it like that. So we are here matching. So we are here basically saying if this variable holds either a variant of south or north, then it will print out south or north. Now, in case it's not any of these variants, then it must be west, right? So we can print out here west. Let's see. And as you can see, the variable holds south, so this will get matched, so this will get printed out. Match is an expression, so we can use it in assignments. Over here we have a Boolean value. Fill the blank with a match expression. Boolean true, binary 1. Boolean false, binary 0. So what we want to do is we want to match this variable over here. And then we provided the cases. So if it is true, then we should return 1. Otherwise, we return 0. So that means the return value over here will then be assigned to this binary variable. Let's store that as U8. And that means binary should then hold 1, right? Because we are matching here true. And then the return value should be 1. Using match to get the data and enum variant holds. Again, we have the message enum. We have seen that before. Then over here, we have an array of message variants. Over here, we are iterating over this array and passing it to this function. As you can see, the argument should be of type message. So we are then matching this provided argument. So we want to match over here message move. Now, as you can see, the message move has struct-like syntax. So we have to match it like that. And as you can see, we want the variables A and B. So let's do that. as you can see, it holds fields x and y. And that means we will then destructure these values into the variables a and b. So a should hold 1 and b should hold 3. Then we match over here the message change color variant. As you can see, this is a tuple-like variant. And this tuple has 3 elements, so we can provide it some variables. And we use here RGB, red, green, blue, and this is for color representation. So in that case, G, the second value, should be 255. And the last value, B, should be, in this case, 0. And again, because we have to match all the cases, if there is anything else that doesn't match here, we will print out no data in these variants. Like that. Matches. Matches looks like match but can do something different. So the macro matches allows us to test, for example, this array if a pattern matches. So as you can see, we are iterating over the elements of this array. So over here we have the assert macro, and all this does is it asserts that the given argument evaluates to true. So we can over here use the matches macro, and we provide it AB, meaning the character we are iterating over. And then we can give it a pattern it should match. So as we are iterating over each element over here, it should match each of these characters. And we can do that like this. So we want to match characters from A to and including Z, or A to and including Z lowercase, or 0 to 9. And notice these are characters and not integers because we have here an array of characters. Let's see. And this succeeds. As you can see, all we did is we iterated over each element and we checked over here for each element if it matches this pattern. And in this case, everything matched because assert didn't panic, right? Because if one of them would evaluate to false, assert will cause the program to panic. Let's see exercise 5. So over here we have an enum with 2 variants, foo and bar. Then here we have a count variable, which is initialized with 0. And over here we have a vector. Now we didn't cover vectors yet, but they are very similar to arrays, but their size can shrink and grow, meaning a vector is dynamic in its size. So as you can see, we are having a vector of my_enum variants, 2 of them foo and 1 bar. So this is a vector holding types of my_enum. Then over here we are iterating over the elements of this vector. Now we want to match my_enum foo. And if conditionals don't allow to match for patterns, so we can't use that here. But we can do something else. We can here instead use the matches macro, meaning we take E, the element in the vector we are iterating over, and we match it for this pattern, right? So if the element we are currently iterating over matches my enum foo variant, then we want to increment count by 1, like that. And that means count after this for loop iterating over each element should be 2, right? Because matches matched 2 times, because there are 2 my enum foo variants in this vector. If let, for some cases when matching enums match is too heavy, we can use if let instead. So over here, as you can see, we have an option of type i32. We move the whole match block using if let instead. So as you can see, match is really verbose, so we can use if let instead. And we do that like this. We use the if let keyword and then the pattern we want to match. In this case, sum, and the variable should be I. So the inner value here will get destructured into this variable I. And then we are matching on O. And if this matches, then we want to print out these 2 lines. As you can see, this is much cleaner. And this will get printed out. This is a really long string and 7. As you can see, we here provide I, and I just holds the inner value of this sum variant. Fill in the blank, we have here a foo enum with a bar variant holding a type of U8. Then over here we have an instance of the bar variant holding a value of 1. Now over here again we could do the same thing. We can use if let, and then we match the pattern. So if the pattern is foo bar, then we want to destructure the inner value to a variable I, and we are matching on A. As you can see, this compiles. So we have a foo enum with 3 variants, and only the last one holds a value. So over here we instantiate the foo enum with a variant of Q's and a value of 10. I hope I pronounced that correctly. So remove the codes below using match instead. So if I run this code, then this would actually work because we are using if let here. But we can do it in a match statement. So we match on A, right? And then we can provide the pattern. So in case of foo bar, then we would print out this line. In case of foo bas, we want to output this line. And in case of anything else, like that, we print out this line. Now I can delete that. And as you can see, much cleaner. So in this case, match others. Shadowing, fix the arrows in place. Again, we have here an option with an inner value of I32. Then we are here using iflet to destructure the inner value to age. And that means we are actually shadowing age, because as you can see, this variable here has the name age, and we are then destructuring into a variable age. So that means age has been shadowed. Create a new variable with the same name as previous age. Now over here, as you can see, age would be some 30, which is wrong, because we are actually here destructuring it, right? So age doesn't hold some 30 anymore, but it will hold 30, because we are here destructuring it. The new variable age goes out of scope here, right? So this variable over here goes out of scope. And a match can also shadow a variable. So we can here essentially doing the exactly same thing like in the iflet statement over here. And as you can see, this would be the output from this match here. All right, see you in the next topic. So let's see patterns. We can use this sign to match several values, and we can use this one to match an inclusive range. So as you can see, we have here a function match number, which takes an integer as argument. Then we are matching this integer, and if it is 1, then we'll print out 1. And fill in the blank with this, don't use ranges. Okay, so we have to match here 2 to 5. So we can do it like that. And this pattern is basically saying if n is either 2 or 3 or 4 or 5, then we will print this. Match an inclusive range. So if n is between 6 and 10, where 10 is included, then it will print out that. And for any other case, because again in a match statement we have to match every case, so in this case we will print out that. The add operator lets us create a variable that holds a value. At the same time, we are testing that value to see whether it matches a pattern. So let's see, we have here the point struct that has 2 fields with I32 types. Fill in the blank to let P match the second arm. So we have to complete here something. We have here an instance of the point type. Now let's see the match here. So we match on P, and as you can see, this is how we would match a struct. So we provide the struct name and then the fields. As you can see, we are matching X and Y. So if Y is equal to 0, that means this arm here matches, and this will get printed out. And we then can use X over, because this is actually a destructuring assignment. So this would be the same as writing it like that. But this is shorthand syntax. So we are then using X here. Now in the second arm, as you can see, we are matching X and Y fields. So X should be between 0 and 5, 5 included, and Y should be either 10, 20 or 30. Now, as you can see, when we are matching here this pattern, we can't use X. We don't use X here. but we can in fact use y, because we are using here the add operator. So this means we are destructuring the variable y of the field y. So that means the value that y is holding over here will get destructured into the y variable. And at the same time we are testing y if it is matching this pattern. And the last arm, as you can see, we don't match for any pattern other than this main pattern, and then we can use x and y, because again this would be the same as writing it like that. All right, now we want to match this second arm. That means we have to provide values that match these patterns. So let's see, x between 0 and 5, so let's do 3, and y 10, 20 or 30, I will do 30. As you can see, this second arm matched. Fix the errors. Over here we have the message enum which is holding one variant with a struct-like syntax. As you can see, this has one field ID of type i32. Then over here we are instantiating this variant, so this will be an instance of the message enum. And then over here we are matching this instance. So if it is hello, then we match the ID field. So is it between 3 and 7? Then we want to output here the ID. Now the problem here is that we did not actually destructure this field here into its distinct variable, right? So we have to provide here a variable. Let's do ID, because that's the one defined here. And for that we have to use the add operator. So we are destructuring and matching the pattern at the same time. And over here, this is already done. As you can see, we can also provide a variable with another name, as you can see. So the value of the ID field then will get destructured into this new ID variable, right? It doesn't have to be the same variable name as the field we have. And again, we are destructuring and at the same time pattern matching, and that is the reason we are using the add operator. And as you can see, when we are matching like that, then this ID over here got destructured, because this is the shorthand for this. All right. And when we have a pattern here, we have to wrap it inside parentheses. That's also important. And as you can see, in this case, the first arm matched, right? Because ID over here, the value is between 3 and 7. A match guard is an additional if condition specified after the pattern in a match arm that must also match along with the pattern matching for that arm to be chosen. Fill in the blank to make the code work. Split must be used. Alright, as you can see, we have here an option with an i32 value. Then we have here split, and we are here matching the num variable, and we are doing that to basically destructure the inner value. So we are putting the value of 4 into x, right? So we can then use x over here. But we over here also want a match guard to check if x, in this case this value over here, is less than split. We can do that like this. So this basically is just for destructuring this value into x, and over here we have an additional conditional, a match guard, to check for a more specific condition to be true. So if num is a sum, so if num is of some variant, then we destructure x and check it again. And if all of that matches, then we execute this. If it is a sum, but the value over here is actually bigger than split, then this will get executed. And if num holds a none, then we just return a unit type, ignoring remaining parts of the value with this. So as you can see, we have here a tuple. I won't annotate that. So we are matching on numbers. Now we only care about the first, as you can see, and the last one. So what we can do over here, we are matching on a tuple, right? So this is a tuple, and we want to destructure the first and the last values into the variables first and last. We can do it like that. Right? So we have the first, then anything in between, and then the last. So first should hold 2 and last should hold 2048. Using pattern mutable reference to v to match a mutable reference needs you to be very careful, due to v being a value after matching. Let's see, fix the error with least changing, don't remove any code lines. So over here we have a mutable variable holding a string. And this would be a variable that holds a mutable reference to a string. Now we match R, and that means over here we can destructure it directly into a value like that. So this string over here will then be destructured into the value directly. We don't have to match mutable reference like that, right? And that means the value variable will hold a mutable reference to a string. And of course, then we can modify the string over here. All right, that's it. See you in the next one. A method is a function that is associated with a particular type or struct. It takes parameters and returns a value, like a function, but it's defined as a member of a struct or an enum. It's called using dot notation, like accessing members of a struct, and it's implemented through an implementation block. Let's see an example. Over here we have the struct rectangle with 2 fields. And as you can see, we can then implement methods for this rectangle type using the impl keyword and the name of the type we want to implement the methods for. So then over here we can see that rectangle has a method called area. It takes as an argument a reference to self, and self stands for the name of the instance. So inside the method we are multiplying self.width, this field, by self.height, this field, and then we return the result of this operation. Now again, self over here will be replaced by the name of the instance. So when we create an instance of rectangle with concrete values, then as you can see, we can call this method on the created instance, rect1. Meaning, when this method is called like that, then self over here will be replaced by rect1. So here rect1.width times rect1.height, meaning 30 by 50 will be returned. Now let's see associated functions. An associated function is a function that is associated with a struct or an enum, but doesn't take an instance as its first parameter. So you can recognize an associated function if it doesn't take self as its first parameter. It's called using the name of the type, not an instance of it. And it's often used as constructors for a struct or an enum. So let's see an associated function. As you can see, we have again the rectangle type. And we implement over here again in an implementation block the new associated function for the rectangle type. And notice we don't have self here, and you will see in a minute why that is. Now the new associated function takes two arguments, width and height, both of type U32, and it will then create an instance rectangle and returns it. Meaning, when we want to call this associated function, we don't call it on an instance, right? Because we don't have self here. We call it directly on the type. So in this case, we take rectangle, double colon, and then the function new, and we provide it two values, 5 and 10, right? That means rec1 will then hold an instance of the type rectangle. Okay, let's do the exercises. We will skip this example because I've showed you that before. And we will do the exercises directly. Methods are similar to functions. Declare with fn, have parameters and a return value. Unlike functions, methods are defined within the context of a struct or an enum or a trait object. And the first parameter is always self, which represents the instance of the struct the method is being called upon. So as you can see, we have the rectangle struct again. And over here we have the implementation block. We can implement the methods for this type. Now, as you can see, we instantiate rectangle over here with concrete values and then assign it to rect1. So rect1 holds an instance of type rectangle. Then over here we call the method area on rect1, and we should get back 1500. So let's implement the area method. So the first thing is we always start with self. So every method takes as first argument self, okay? Then the return type will be a U32, right? Because we are here doing operation with these two fields. Now, what we want to do to get the area of the rectangle is multiplying the width by the height. So we use self.width times self.height. And I omit here the semicolon, so this will get returned. Let's see. So when we call the area method on the rect1 instance, then rect1.width times rect1.height will result in 1500, meaning 30 times 50. Self will take the ownership of current struct instance. However, reference to self will only borrow a reference from the instance. Let's see, we have again the struct traffic light with one field. Now over here there is the implementation block. We can implement methods for this struct. Now using self to fill in the blank. So we have been using self like this, right? Meaning we take a reference to the instance. Now this is actually syntactic sugar for this. And as you can see, self with an uppercase S refers to the type we are implementing the method on, right? So in this implementation block, when we use self uppercase, it refers to traffic light. And you can use this syntax, or you can use, like we did before, using just self, right? And here we want to take a mutable reference because we are here mutating the color field. And again, and this and that are exactly the same, but this is not mutable. So if I would do it like that, then as you can see, these are actually exactly the same thing. But I would suggest just stick with that. It's more readable and it's clear what you mean. Associated functions. All functions defined within an impl block are called associated functions because they are associated with the type named after the impl. We can define associated functions that don't have self as their first parameter and thus are not methods because they don't need an instance of the type to work with. So as you can see, we again use the traffic light struct, and here we have the impl block. So let's see, first implement an associated function new. It will return a traffic light contains color red. Must use self, don't use traffic light in fn signatures or body. Let's first see in main what's going on. So we call here the new associated function. And this associated function is associated with the traffic light type. And again, notice the difference is we call this directly on the type and not on an instance. Otherwise, it would be a method. So we call new, and then we want to have an instance of traffic light back. Right? This new function should return an instance of traffic light, meaning we can then call upon this instance light the getState method and return red. So let's see. Over here we are expecting no argument, right? So let's leave it like that, and remember, associated functions don't take self. Now the return type would be traffic light instance. And because we should use self in here, we can do that. And again, self in an implementation block refers to the type. In this case, traffic light. Then in there, we want to create an instance of traffic light. So again, we can use self instead of this name. And then we, like normally instantiating it, providing it concrete values. So in this case, we want the self.color field to hold a string of red. like that. And as you can see, then we should get, and as you can see, when we call this associated function, we will get back an instance with this concrete value, a string red. Then we call upon this instance light the getState method. So again, self here refers to light because we are calling the method on this instance. And it takes just a reference to the instance, meaning light is usable even after this method call. And all it does, it will return the value inside the color field of the instance, in this case light. So light.color will hold a string of red. Multiple impl blocks. Each struct is allowed to have multiple impl blocks. Again, rectangle struct, and using multiple impl blocks to rewrite the code below. So we can either put all of the functions and methods in the same impl block, or we can even reorganize it using various different impl blocks. So we can, for example, put that in its own implementation block, like that. And it will work exactly the same. This is just for organizing and restructuring. Enums. We can also implement methods for enums. So over here we have the enum traffic light color with 3 variants. Implement traffic light color with a method. So over here in main, we are instantiating traffic light color with a variant of yellow. This would be the type annotation. And then when we call a method color on the C instance, it should return yellow. So let's see. So we could implement that using a match statement. Then we match self, and if match self would be this, then we return the string yellow. Okay. And we can over here, instead of writing the whole name of the type, we can again use uppercase self, referring to the type this method is implemented on. In this case, traffic light color. And remember, in a match statement, we have to handle all the possible cases, meaning we have to create an arm for red and for green too. So let's do that. Let's see. And as you can see, because we have here an instance which holds the variant yellow, we will get back yellow when we call the color method. All right, that's it. Until next time. Until now, we have only been dealing with concrete types, but we can also deal with generics. And generics are placeholders for concrete types. It enables writing more reusable and flexible code, and it avoids having duplicate code for different types. It's a zero-cost abstraction, meaning the Rust compiler will at compile time fill out the generics with concrete types. And there is also a concept called const generics. I will just briefly touch upon it because this is more of an advanced topic, but I will show you one exercise just so you get the idea from it. So a const generic is a type parameter that represents a compile time constant value. It allows to write generic code that operates on values that are known at compile time, and it's mainly used for array sizes, bit widths, and other constants. And you will see what I mean when you see the exercise. Let's start with generics. So as you can see over here, we have a struct A. Now this would be considered a concrete type because we don't deal with generic types in here. Now the struct S takes as an argument an instance of the struct A. This is also considered a concrete type because again there are not generics used here. Now the struct sgen is considered a generic type because we are dealing here with a generic type parameter, and this would be the notation when you declare a type, for example, then after the name of the type you annotate a generic type parameter like that using these symbols over here and then providing a name. And by convention, this is usually T, standing for type. And that means this struct can hold any type. Now, as you can see, we have here some functions. This function over here takes S, which is a concrete type. The gen spec T takes as an argument an instance of sgen with a type of A. Now again, A would be a concrete type, meaning the type parameter over here is specified to be a concrete type. So we can only pass to this sgen struct an instance of the struct A. Then over here we have the genspec i32 function, which takes as an argument the sgen struct over here with a value that is of type i32. And over here we have a generic function, meaning we are declaring after the function name the generic type parameter T, and then we can use it on here, meaning that we can provide as an argument over here an instance of sgen with any type. So let's see, using the non-generic functions. So these over here are all non-generic, as you can see, because we didn't define a generic type parameter. And all the values it is using are concrete, right? Over here we have S, over here we have sgen, and this is taking as a value T over here the concrete type A. And over here it takes as concrete type i32. So all these are non-generic functions. The only generic function over here would be this one. So let's see. So we want to call the regfn function. And as you can see in the function signature, we are taking as an argument a type of S. So let's provide that. Now we have to pass into S the concrete type A, right? Because that is defined in this struct. Then gen spec T. So this function over here takes an sgen struct with a type of A. Now again, A would be a concrete type. So we provide here sgen and A, right? So we are passing to the sgen struct over here a value of type A. And in this case, we want it to be sgen and let's say 7, because over here we define that this function should take as an argument a type sgen which holds an i32 integer. Then explicitly specify type parameter char to generic. So over here we are calling the generic function, meaning we can pass to it an sgen type holding any possible type. Now we can explicitly specify a type parameter for this t over here, and we are here saying t should be a char, meaning we are calling the generic function over here with the type sgen and passing as a value a type of char, let's say a. And implicitly specify type parameter char to generic. So we don't have to annotate the type here, it will be automatically inferred by the compiler. So if I do the same thing over here, let's go with Z this time. As you can see, this is compiling. Now again, because sgen is defined to be generic over its type, pass any value. So let's pass, for example, a floating point. As you can see, this is also compiling because t over here is a placeholder that stands for any type possible. But again, when we annotate the specific type, then we can only pass a character in this example. So if I try 7.7 here, this would be a compiler error. If I define F64, as you can see, then it's working. All right. A function call with explicitly specified type parameter looks like that. And this is also called the turbofish syntax. So let's see, implement the generic function below. So as you can see, we are calling here the sum function with different types, and that's the whole point of generics. So here we are calling sum with two i8 integers. Over here we call the sum function with two i32 integers. Remember, if nothing is annotated, then the default integer type is i32. And here the same thing, but for floating point F64. So we have to use here generics, otherwise this won't be possible. Over here we are creating our generic type parameter, and again by convention this is called t. Then we take here the arguments. So let's say a should be of type t and b should also be of type t, and then we return a type of t. Meaning, if we pass here two i8 integers, then t will get converted to an i8, right? This is just a placeholder. And because we operate then on two i8s, the return type will also be i8. So what we do is just adding together the two arguments and return it. And over here we have to implement a trait bound, and we'll cover that in the next section. So we have to define here that t should implement the add trait, otherwise we can't use this plus sign over here. And again, we will cover that in the next section when we look at traits. And as you can see, this is compiling. So we can pass to sum two numbers of any type. Let's see number 3, implement struct point to make it work. As you can see, we are instantiating 2-point structs, but over here we are passing to the fields different types. So in the first instance we would have I32 values, and in the second instance we are dealing with floats. So to make that possible, we have to use generics. So let's implement the point struct. And we are defining here the generic type parameter. And then we can define the fields. And as you can see, the fields hold the type T. Meaning, if we pass it integers, then x and y must both be integers. If we are passing it floats, then both of these fields must be of type floats. Now, because we are here defining a generic type parameter, this parameter over here becomes part of the type annotation. So over here we are providing to the fields of the point struct values of type I32. So we must annotate that. And over here we are passing F64. And as you can see, this is compiling. Now again, we don't have to do the type annotations actually. I just want to make that clear. As you can see, the compiler is able to infer that for us. Modify the struct to make the code work. Don't modify this code. So as you can see, we are here instantiating a point, but the fields over here hold different types. So this is not working because T over here defines that both of these placeholders will be filled with the same concrete type. So in this case, if we are passing x over here with an I32 type, then the compiler thinks that y should also hold an I32. Now what we can do then is defining another generic type parameter. And by convention, you just go one letter further. So T and U. Meaning we can then use here U, right? And this indicates that the fields over here hold different types or could potentially hold different types. They can also hold the same types. And then when we annotate that, we have said that the generic type parameter becomes part of the type annotation. So we would pass here for x, so we would pass here for T and I32 the value, the type the x field is holding, and over here a string. So this would be the type annotation for this returned instance. Number 5, add generic for val to make the code work. Don't modify the code in main. So here we have the val struct holding one field, and we have an implementation block implementing one method for the val type. Now, how do I know it's a method? Because it has as first parameter the self keyword. And all this value method does is just returning a reference to the val field value. All right. So when we instantiate the val struct over here, we are providing it a type of F64. But over here, we are instantiating the val field with a string. So again, we have different types. So let's annotate here the generic type parameter. Then we can use T here, meaning the field val can hold any type. So let's annotate here. Now over here, as you can see, we are returning the value of the val field, and we define here that it should be of type F64. Now this would cause an error, because when we call over here the value method on the instance of y, then self.val would hold a string, right? So it doesn't return an F64. Now we have to use a generic type parameter also in this implementation block, and we can do that like that. So we have over here the generic type parameter for our type, and as we've said, this becomes part of the type annotation. And over here we are also defining a generic type parameter t, so we are then able to use it inside the implementation block. So over here we can define that it should be a reference to t, right? A reference to any type that the val field holds. So in the first call of value, it would be an F64, right? That is the type of the returned value that val field is holding. And in the second call over here, it would be a string, right? So t then would be string. Number 6, we have here a point struct, and we are here defining that the fields could potentially hold different types, but they could also be the same. And here we have the implementation block for our point struct. Now, as you can see over here, we are instantiating a point with i32 values. Right, so they can be the same. Even if we here have two generic type parameters, it doesn't matter. They can be the same. But over here we are instantiating point with two different types, right? We are instantiating point with a string literal, this here, and a char, that over here. So they are different in its types. Then we call over here the mix-up method on P1 and provided an argument of P2. And then over here, as you can see, we want then P3 to look something like that. So we want the newly created instance here, P3, to hold the value of the first instance, in this case P1. As you can see, we are taking x from P1, and we want the y field to hold the value of the P2 instance, this character, right? So how would we do that with generic type parameters? Now, let's first implement here the mixup function. And again, the convention is just the more generic type parameters you are declaring, you just go further in the alphabet. So T, U, V, W, all right? And as you can see, as a first argument, we are taking P1. Now let's take ownership. We don't care because we don't use P1 after this point, meaning we can take ownership and we don't have to use a reference to self here. And as an argument here, we want P2, meaning a point with generic type parameters we are declaring here. And the return type will be a point with a generic type parameter t and a generic type parameter of w, and you will see why that is. So then what we want to do is creating here a new instance, and we provide here x, which should be of self, because self here refers to p1, right? So we want self and we want the x value, and y should take it from the second argument, the p1 over here, and we want the y field. So let me actually annotate that as other. Right, we take here another point instance, and this would refer to p2 because we are passing p2 over here to this mix-up method. So we take from p2 the y field, and then we are returning this instance, meaning p3 will then look something like that, right? So let me annotate the type. We would have a point with the x value of p1 and i32 and a character type of p2, the y field, right? And that is what we will get. Let's first see if this even compiles. And this is compiling. Now, as you can see, we have here a lot of generic type parameters. So when we take a look at the mix-up method, as you can see, we are here declaring new generic type parameters because we want to define over here that the types self, and self again refers to the instance over here, p1, that these types are different from the types provided on the second argument, the instance of p2, right? If we compare it together, then p1 instance holds different types than the p2 instance. So we need new generic type parameters because t and u are for this p1 instance, and the argument we are here providing, p2, will hold different types, right? And as you can see, we are then taking from p1 the x field, and from p2 we take the y field. And this would be the return type, a point with t, this is from p1 x, and w, this would be the second type from the p2 point. All right. Fix the errors to make the code work. As you can see, we have here a struct point which has two fields which are generic over its type. And we implement over here a method for the point struct over here. Now this method over here is in fact only implemented for a struct point that holds f32 types of fields, right? So if we would pass floats, then this method is not implemented for point. So this is only implemented for point with a concrete type of f32. Now, then over here we are calling on the fields x, the power integer method. And let's see that in the Rust documentation. So as you can see, the power integer method over here is actually implemented for F64 types, right? So self in this case must be of type F64. As you can see over here, we have X which holds an F64 type. So we can call this method on X, right? Again, this is a method and not a function. So the problem over here is that self in this case would be F32, which is not the right type. So let's change that, F64. And that means self over here would be of type F64, the concrete type we are providing here. And then, of course, the return type would be F64, right? Because we are here performing an operation on two F64 types. Now, over here, of course, we have to provide floating point values, right? Because again, this method is only implemented for a point that holds as fields F64 types, like that. Right. And then we can use this method as defined in the standard library. And of course, over here, we just have to annotate one type, right? Because we only have one generic type parameter. And as you can see, this is compiling, and I will see you next time. So I've told you that we will take a brief look at const generics, and I will just solve one exercise and leave it at that, because const generics is a more advanced topic.